Good morning, good afternoon, and good evening to everybody. Welcome back to our last day of our cross-disciplinary education research conference. Today's programming will start with our keynote speaker, Dr. Kathy Perkins. Dr. Perkins is an associate professor in physics in University of Colorado Boulder. She's also the director of PhET Interactive Simulations project and the director of University of Colorado Science Education Initiative. Dr. Perkins received her bachelor's degree in physics, master's in chemistry, and PhD in atmospheric sciences from Harvard University. And she joined the PhET project in 2003, and then since 2008, she has been the director of these efforts. Her education research has focused on pedagogically effective design and use of interactive simulations, sustainable course reform, students' beliefs about science, and institutional change. Thank you so much, Dr. Perkins, for joining us today, and we all look forward to your keynote presentation.
Thank you very much. It's great to be here and to have the chance to talk with everyone. Let me go ahead and start by sharing my screen. So can everybody hear me okay? We're good?
That's good.
Okay. So today I'm gonna focus on a new effort we have around expanding what simulations can do and how they can fit into the education ecosystem, and also can inspire new ways of doing research and new opportunities around researching interactive simulations. I'm going to start with just a super brief introduction. I think most people are familiar with the basics of PhET since we've been around for a while, but we are a project that started in 2002, and we have both a product development side where we're designing and building and disseminating interactive simulations. And then our group has a research side where we're looking at the design of a simulation specifically, but also looking at how simulations can be integrated into the classroom and how that can impact student-student interactions, teacher-student interactions, and interactions between students and the content itself. I want to give you some examples of sort of where we're going when we redesign simulations from their original legacy version into HTML5. We have been engaged in this process since 2013. And we did a lot of learning between 2002 and 2013. So we've been implementing that learning as we redesign and redevelop the simulation. So for those not familiar with the simulations, PhET simulations have lots of different options to do. They're kind of an open exploratory space where you can do things that you engage in experimentation to discover concepts. For instance, here, the relationship between speed and energy. In many of our new simulations, we have these additional measurement and representations. For instance, here we have a new measuring tool where you can go ahead and measure energy at different points along the track. And we have a whole new screen that is focused on graphing. And here you can look at two different, sorry, something's in the way, close it. Two different kinds of graphs, either energy versus position or energy versus time. The other simulation I wanted to show you was the natural selection simulation. So while we haven't had a big graph in a big grant in biology, we do have some specific simulations for biology, and I just wanted to welcome the biologists and biology education researchers to explore these types of simulations. So in this one, you can decide what mutation, whether you want the brown fur mutation to be dominant or recessive, and then you can see how that emerges over the course of different generations, and you can look at different sorts of things like the pedigree of this particular bunny who had a mutation. You can look at the proportion across different generations, or the population graph, again, taking out a data probe now and being able to take data along the way. You can add limited food so the bunny population doesn't get out of control, and you can go on to the next screen, where you then have additional mutations you can play with around ears, which basically has no impact, and teeth, which is a selector for tough food. So we are continuing to bring simulations to HTML5 as we have resources. The goal is really to provide a tool that can simultaneously address multiple goals in instruction, both content learning, process goals around experimentation, data collection, questioning, reasoning, modeling, those sorts of things. Create a tool that students find enjoyable, engageable, understandable, really working on that sort of affective goal, and then something that can be disseminated freely and easily, basically around the world. Today we have 158 simulations, 85 in HTML5 right now. 2,000 sim-based lessons have been shared to our lesson database. And if you do create lessons, I invite you to add yours to the collection. They're used at K-12 and college. They're all open educational resources. They're translated into 90 languages, and they run online or offline. This is the usage curve. I didn't have a chance to update it, but now we're up to 200 million simulation uses per year. That's really up about double from last year, primarily due to COVID. We've had expansions over the years into different content areas, and we do hope to continue to expand our collection. We've also had technology advancement. So one of the first was making the sim translatable, then HTML5, then working on creating additional accessibility parameters around description and sonification. And I'll show you what we're also doing with sort of PhET.io project. They do have global impact. Right now we're 50% international. And I just wanted to show you sort of some of what happened at COVID, when COVID hit last March. So this was in France. Yellow, orange is last year, blue is this year. And we definitely saw a huge uptake of the simulations as the students moved to remote learning, which we were pretty excited to see that as an indication that the simulations were helping to keep students learning science and math during this challenging time. We've also had a surge in sort of research that uses the PhET simulations. So this is a plot of from Google Scholar of just a search of PhET simulation education articles. These aren't all in research journals, but what we've seen is a growth since we moved to HTML5, and especially a growth around in international research. And we see the research really probing many different things. It probes student learning, but it also probes problem solving, affective experiences around science and math. It really ranges. And one of the goals of this new initiative is to expand the kinds of questions and research you can engage in and answer with PhET simulations by providing additional flexibility of the simulations and research data out. So I want to move to focusing on introducing you to these next generation PhET simulations. You've seen the HTML5 ones on our website, but I want to give you a bit of a history. We really wanted to envision these next generation PhET simulations as being driven by what we already knew about how PhET simulations worked, how they were designed, how teachers were leveraging them. But we wanted them to go beyond what they were able to do back when they were just Java and Flash. And so we also engaged and looked at the community needs. So we, back in 2014, we held a stakeholders meeting that included educators, learning designers, assessment professionals, researchers, both in DBER and the learning sciences, inclusive design and accessibility experts, and education technology companies. We brought them together and really envisioned sort of the capabilities that we wanted to bake into the new simulations. So we have, we have two different styles of simulations. We have the PhET simulations you find on our open accessible website. So these,
Kathy,
yeah.
Kathy, I'm sorry. There is a gray bar across your slide at the top, right where your mouse is right now. Yep, now it's gone. Is that?
So yeah, maybe somebody, I don't know why it's there. I mean, I know sometimes the Zoom, it's a Zoom thing, but I don't know how to turn it off. It's the one that says admit, like, you know, when people are in the waiting room.
Okay.
Does anybody
Stephanie, do you know
how to like not have that pop up for me?
You should be able, there's a caret or an arrow to close that notification box. Should be up at the top.
Well, I closed it, but
is there a full screen option?
well, I'll just keep closing it when it pops up there.
Can you X out of it?
Is there also
There we go. That's better.
I mean, yes. So please tell me if it reappears. But last night I was on Zoom and that gray box wasn't appearing. I thought it was.
Thank you.
I thought it was gone, but thanks for letting me know. So with these next generation PhET simulations, we have the HTML5 goal of bringing these simulations to be usable on all devices, including phones and tablets, translatable, embeddable, and highly accessible, which is a project in progress. And those are the 87 sims you see on our website. We also was envisioned was the ability to customize the simulation. So really hide and show anything on the simulation, set the starting state so you can match it to your learning or instructional moment, design a test feature, you know, being able to use it in assessments to make it interoperable so it can talk with any education technology that you have. You can set the state from that technology. You can pull the backend data out of the simulation into that technology. So you can really start to think about how to create a full learning environment and sort of watch what students are doing in that learning environment. So you don't just know how they answered your questions, but you actually can see inside what they're doing with the simulations themselves. So I want to give you a little bit of a tour of what this new technology looks like. It's called PhET.io. And you can customize the simulations. So I'm going to start with just a basic demo. You can make it just one screen, which you can do with other simulations. You can hide or show controls. So let's say you don't want students to see this photon view, you just want them on the beam view. You can completely hide those controls. You can set the starting state if you want them to start with the filter on, and you can modify labels. We've gone beyond, this is just a demo. I want to give you a little bit of what it actually looks like. So this is natural selection in our new PhET.io studio. So this is exposes the inner workings of the code to an instructional designer at a level that they can actually, I know it looks like a lot, but you can actually pretty easily come to be acquainted with this. So each screen has the model and the view. The view is anything that's visible. So let's say you want to create a situation in this simulation where you want to start with no wolves. So you would go to the environmental factors panel, go to the wolves checkbox, and you can just make the wolves checkbox invisible. So now that's your setting. And let's say, you want to have this population graph, but you don't want students to get distracted by those other graphs. You can just then go to the graphs, the choice radio button, and make that entire thing invisible. You can preset the mutation to have a brown dominant mutation, and then you can launch the simulation in that specific mode. So as you embed it in your activity, it would come up in this setting that you had configured, and then the students would be able to use it in that. And this could be embedded as an iframe in a full activity. So that is sort of the full customization. The integration, we allow data to be pulled in and out, and I'm just gonna kind of show you an example of this virtual lab. So you can customize again just down to one solute. Here you can shake in, and this is monitoring the student to see if they can make a saturated solution. And when they do make a saturated solution, the external iframe can detect that and give them feedback. So these new features allow you to create, to monitor what students are doing and explore the role of hints or feedback in that learning process. And then you can record data out. So you can build, this is an external data record button. Every time I press it, it goes back to the sim and say, hey, give me your data. And then the external website just puts it into a table. So you can record out data. You can record out actually the entire state. So I can revisit any one of these previous data points I got and push it back into the simulation. And you can also, if you want to get into the details, log backend events. So, sorry, I just keep closing that. So every event or interaction the students do is logged through it's called a JSON log file, but you can imagine it generates a whole lot of data as you detect what students do. You can also capture the states, which tells you what the state of the simulation is, but it doesn't tell you how the students got there. And you can capture input events. So where the mouse is, what the mouse is doing. And right now these mouse events are being played back into that lower copy of the simulation on the lower right. So that's the suite of capabilities that were envisioned by this group of cross-disciplinary sector stakeholders. And we are now essentially on the verge of realizing many of those features. Accessibility is in the work. It's a challenging, it's very challenging. And then we've also realized a lot of these more advanced features, and we're working on growing the sim collection we have in that. So by when you embed simulation now into a learning environment, you can think about the new opportunities for learning and research. So I mentioned sort of, you can monitor what students are doing, think about the role of feedback in activities or assessments. You can probe, you can think about what can you measure now that you couldn't measure before, because you can actually see students' action, and you can explore that backend data and probe what, what patterns of interaction lead to productive learning, or what patterns of interaction indicate that students are proficient at this sort of science practice or that sort of science practice. And it provides a lot of instructional opportunity for designing, new challenges for students by setting the simulation up in a particular state. So this is just an example. Andy Garvin had built out this nice sim-based lab that included both process and content goals, where he had the Hooke's Law simulation and students were collecting data in a spreadsheet. But now you can imagine that you could customize the sim, you could design an instructional wrapper, you could follow students' actions, you could provide adaptive feedback, and you could assess on both process and content by embedding this in some sort of learning platform. So I want to give you some research examples now of collaborators that have been using these new capabilities of PhET.io simulations. This is sort of was inspired before we fully got PhET.io, but we were logging back in event streams. So Julia Chamberlain was a postdoc with PhET, and in this study, we looked at the effect of guidance, different levels of guidance on the way that college students interacted with the simulations. So they were engaging in the simulations in their lab sections, and we recorded out a log of event streams of user interactions and then analyzed that log. We went from sort of light guidance, where we asked students to explore the sim, make sure to investigate all the factors, to moderate guidance, where we, had a little bit more direction, compare strong and weak acid, describe all the ways that they're similar and different, but still pretty open. And then heavy guidance, where students were more told what to interact with and what to do within the simulation. And we definitely saw an impact in students, the level of student interaction with the simulation. So the students that had the light guidance had the most interaction with the simulation, and the students with the heavy guidance had the least. The students with the light guidance also explored almost 100% of the features within the simulation on their own. The moderate guidance as well, and the heavy guidance was really impacted. If you didn't tell them to explore it, they did not explore it. So that told us a lot about the influence of heavy guidance on how students interact with simulations. Ida Roll is a learning scientist, and he has gone deeper in this direction and used leveraged learning analytics in his research. So this is a study that he did with 100 first-year college students in the introductory physics courses, again with two different levels of scaffolding. We called it guidance, he calls it scaffolding. It's essentially the same type of, it's very similar. He logged 100 hours of data from these student users, and that was 130,000 actions, just to give you a sense of how much data is generated by a simulation. The study was structured as a pretest to understand their knowledge about circuits. Then two conditions, students first in this activity. One, they either did an unstructured activity or a directive activity. And then in activity 2, all of the students did an unstructured activity. And then the post-test measured both their understanding of activity 1 and their understanding of activity 2. Unstructured activity was similar to what I showed you about Julia's. Pretty open, use the simulation to explore how voltage, current, and brightness depend on the number and arrangement of light bulbs. Structured, similar learning goals, but as you can see just from the look of this, it was much more structured, had explicit data tables. They were asked to build specific configurations of light bulbs. he looked at a variety of things. I'm just going to give you a sense. It's a very deep study, and encourage you to go look at this paper. That was in instructional science if you want more information. But first, on the impact of learning, he did see sort of the impact of learning on low. This was selected for the students that had low pre-knowledge. So under the directive case, those students did learn, but they actually learned a little bit less than the students that came in as low pre-knowledge but had the unstructured activity. And then they all ended up about the same. But essentially the bottom line is the unstructured activity was probably addressing many more of the kind of process goals that you would have in science learning, and they learned just as much. He explored whether the backend data could indeed predict learning from the simulations. And he found that after about 5 minutes, the log file of, if you did models with the log files, you could predict learning. So this was the percentage of interactions observed. Examples of 3 different sorts of models. He studied many different model combinations of the backend data. But you can see at about 10 minutes, he was 65 to 70% accurate, not 10 minutes, sorry, 10% of the interaction. He could have a pretty good accuracy of whether they were going to be a high learner or a low learner. And by the end of that those interaction events, it was even a higher accuracy as to whether he could predict whether they were a low learner or high learner. He also investigated what productive students do. So he kind of looked at 3 different types of things: constructing a circuit, pausing, not doing anything, just pausing and thinking, sort of implied in that pause. Testing a circuit with 1 resistor, testing a circuit with 2 resistors, or testing a circuit with multiple resistors. So the beginning of the interaction, so this is the first 240 seconds. So students are constructing, then they go test, then they pause, then they test, then they construct some more. Then they test something more complicated, a resistor with 2 circuits, a circuit with 2 resistors. Then they pause and they build more complex test, pause, or construct. So they kind of going back and forth through these different sort of actions. But then the pattern sort of changes. They start actually pausing more. So they construct, they do another test on this 2 resistor circuit. They pause, they test again, they pause, they think, and they keep kind of going through this pattern, but with sort of longer pauses and thinking. And you can see here that they really focus on this. They test a lot with this 2 resistor circuit. So when he looked at patterns in the data of unproductive learners, he found that these unproductive learners often were testing with circuits that had lots of resistors, more than 2 resistors, and that the pauses came before the construct, only before or after construct. They didn't pause after test, pause before or after construct. And when he looked at productive learners, he saw different patterns. So where they did a lot of testing of 2 resistor circuits and pausing after that. Those are the kind of patterns that he saw when he looked at the backend data, and he was able to pull that out. And that was how, the way, the signatures that allowed him to understand learning. So we've kind of looked at Ito's example shows us how we can look at the impact of learning. We can look at the impact on prediction of learning. and we can dive into sort of what the backend data is doing. And now I want to move on to sort of what these new tools might be able to do in terms of advancing assessment and things that we can assess. Shima was a graduate student in Carl Wyman's group when she did this work. Now she's a professor at Stanford. She was studying how we can leverage this. This is a research tool actually right now. We do want to build it out for full use, but it's a research tool. How we can use the circuit construction kit and specifically this black box version to assess knowledge and practices, give us insight into students' problem solving practices. So I want to give you a sense of how different students can be when they're interacting with this sort of tool. So we're going to take a look at some videos. Ooh, I think I need to unshare. Sorry. I think I did not share this video. Oh, I did. Okay, never mind. So this is Ellen. And I can't find my button. Sorry.
All right, so let's see if the top and the right or terminals are connected electrically.
Yes, just
let's see. It looks like, oh, it is. Is that? So there is current flowing in there. Okay. Does it not show the electrons moving anymore? Okay, that's fine. Let's see if these are connected. 0 amps in there. Okay. What about these? The bottom and the right don't seem to be electrically connected. Okay, so these seem to be though. Yeah. And let's get a voltmeter. So the battery.
So as you can see, Ellen is being super systematic about how she's going through this, this process of exploration. So now let's do a comparison with Gail and Josh.
Nothing is connected, I guess. So I think, okay, let's start with a wire.
Should we just connect things?
Yeah, connect a wire from here to here and see if there's a current. There's no current.
No,
okay, so.
do that for each of them.
Well, how about, I don't know if this is real, but like try to connect it like to all, like just make it go all the way around. You know, like.
Oh, like one?
So get a wire, another wire, and go from there to there. And then another one from there to there. You see what I'm saying?
Yeah, got it.
Okay, and I'm guessing there's still not going to be any current. Okay, great. So there's no current. That means that there's no battery in there.
Definitely not a battery.
So okay.
Has to be some kind of resistor. Like
Yeah, okay, so how about you get a battery and you attach it anywhere, really. Could be anywhere.
the junction.
I think it means there's no battery. I could be wrong.
Yeah.
Whoa. Okay.
So,
That means that there's no resistor in there either?
yeah.
I
well, no,
think.
because here, let's see. Remove that and then do it again. Yeah. It was.
Okay, so hopefully you saw that this sort of task can really provide insight into how students are thinking about problem solving and the way they go about it. If we were to keep watching this, we would see actually the problem solving approaches of this team evolve to be more systematic as time went along. So the other kind of interesting fact about simulations or these sorts of tools is that there can be learning and assessment all at the same time. So Shima coded these interactions from these interviews and looked at different experimentation practices and reflective practices and looked at, how those were displayed within the interview. This research is being extended to see what the backend data can tell us. So that's ongoing work in Carl's lab to now look at the learning analytics and which of these sort of expert and novice practices are able to be kind of done at scale by looking at the backend data. I'm going to leave time for questions. So I want to be sure, though, to thank the funders of the project. In particular, the Moore Foundation has really been a great supporter of this latest work on PhET.io and the new capabilities, new kinds of research that we're engaged in. And we have some new funding from the EDAN Prize that's going to help us continue in this direction. I want to invite you to find PhET, use the simulations, your labs, lectures, homework, contribute your lessons. You can support PhET by downloading the PhET app on your phone. You can always email us. We like to get input from everybody in the community. If you have a tweak to a simulation that you think would be good pedagogically, if you want to engage in collaborations. Specifically, we will be, I think we will have an opportunity to sort of expand our research collaborations around PhET.io. And so if that new technology inspires you to look more at pedagogy around simulation-based learning or learning analytics back in data and research or assessments or anything you can imagine, please do reach out to me and let's talk about that. With that, I'm going to end.
Thank you very much for a great presentation and for sharing your work with us. So we have 7 minutes at least for some questions, and there are a few in the chat box, so I'll start translating them. So first question from Anya Goodman. Are you planning to hold workshops for faculty interested in developing or modifying simulations?
We don't usually hold workshops for faculty to develop their own simulations, but we definitely are interested in engaging in faculty that want to build out new kinds of simulations and happy to write research proposals around that. Usually that requires funding. So I'd love to build out a new suite of biology simulations and engage with a biology education researcher in a proposal if they're interested in that sort of work. Same with data sciences or university-based mathematics, happy to do that sort of work. Building a new simulation for us is a big endeavor, and it costs about $85,000 at cost. So it's not cheap.
Thank you. Another question from Nicole Growlich. Is PhET.io as well available in different languages?
PhET.io will be available in different languages. Yeah. So PhET.io right now it's still emerging, and it's a basis of a sustainable business model we have, because to really leverage PhET.io, you need to have sort of a platform for backend data collection, a learning environment to hook up to PhET.io. So we are working with some partners to leverage PhET.io. I think recently PhET Interactive announced that they're a new partner with us around PhET.io, and so you'll see some of the features leveraged within PhET Interactive. We do want to have a program for researchers where researchers can engage with PhET.io to do research, without any cost. But it does require a license or just a simple arrangement with a researcher.
Thank you. A question from Keith. He says, math guy question, mathematically, a lot of these tasks can be represented by ordinary differential equations. Do any of these simulations have an option to generate an ODE or a system of ODEs to represent the situation? It would be really neat for students to be able to make changes to the system and see how those changes influence the equations or vice versa.
So I think that would be possible with PhET.io, because PhET.io hooks into the model. So you could give students, you could represent the ODs that are representing the model, and give students hooks into it, and basically use the PhET.io hook into the model to, you'd build sort of the external representation of what the ODE looked like, and then you'd create a hook into the model, push that into the simulation, and it would respond to the changes that the students did in the ODE.
Great, thank you. A question from Rebecca. If guidance leads to less exploration or learning, but certain exploration steps are associated with learning success, which does an instructor go with?
I think you should go with what, instruction should center on the learning goals you have. So I think, if processes and practices are important in your learning goals, you should stay pretty open in how to instruct students to learn with, what kind of instructional tasks you give students. But I think there's opportunities there to sort of go meta with your students and reflect on different ways of interacting with the simulation or a tool, and kind of help advance their overall exploratory practices, and show some of those relationships, like this, is it easier to understand this or this? So you can go more explicit on sort of, get feedback from your students. What did you learn? And then go explicit on the learning. But that is sort of the goal of one of our current research projects with Carl, is to understand how to help teach expert problem solving strategies. So maybe check back in a couple of years and we'll have some more insight. I think he's so far, his group and working with Natasha Holmes, they've discovered that asking students to make the decisions is really a very powerful learning moment. Decisions about what to measure, things like that.
Thank you. One more, I think we have time for one more question. Have you looked at how well these reflective and experimental practices that students have been using in the simulation transfer into an actual laboratory setting?
We have, a long time ago, early in PhET, we did a research study that I think provided some insight into that. I wouldn't say we've systematically studied that question, but we did early on, it was like 2004, 2005, we did a study where we had students using the circuit construction kit in lab, and they either used the simulation or they used the real world equipment and did sort of parallel similar activities for the two groups. And then everybody got a learning challenge with the real world equipment at the end. And the students that had learned with the simulation were able to both build the circuit faster or as fast as the students that had learned with the real equipment. So they didn't really have a challenge with building with real equipment. And they actually generated better explanations about how the real equipment was working. So somewhere they had perhaps a better model of how circuits worked, and that really helped them when they turned to the real equipment. So that provides a little insight, but I would say it's probably really content specific and sim specific.
Okay. Thank you so much again. I'm sorry we can't get to all the questions. Thank you so much, Dr. Perkins, for being here with us, and thank you for sharing your work.
Thank you for having me.